Stanford University.
Today is the second and the last lecture of this mini course. In the first one, we did several things. One is we introduced the standard model in quite a bit complexity, several aspects of the standard model. And we discussed some of the great successes, namely that it agrees with all known experiments. And this agreement is accomplished with just roughly 20 parameters of the standard model. And as we may count today, 20 particles, or 20 what are called representations of the standard model. So it sounds like quite an accomplishment to explain all data that were gathered throughout human history from thousands of years ago to today in terms of 20 parameters and 20 particles. So it's an amazing accomplishment. It came into being in the 70s, and by now it has been tested with different levels of precision at all kinds of phenomena, from electromagnetism, nuclear physics, weak interactions, gravity, etc. So that's what we were discussing. Today, what I'm going to do is I'm going to discuss some of the extensions of the standard model. You want to sit? Thank you. Some of the extensions of the standard model. The extensions, as we mentioned, are motivated by some outstanding problems that the standard model faces beyond the problem of economy, beyond the problem that it has too many parameters and too many particles. Namely, why are atoms neutral? That's the first question we mentioned. Why is gravity so weak? And why is the universe so large? So these are three of the outstanding questions we would like to address. I've already alluded to one approach, one geometric approach to the weakness of gravity, which was the theory of large new dimensions. Today I'm going to talk about grand unification to start with. Grand unification is an attempt towards the economy of the standard model, which has been quite successful. It's one of the extensions of the standard model that is both very appealing and has received some experimental confirmation, in particular by accounting very elegantly for the neutrality, electrical neutrality of the atoms, which is called charge quantization. Okay. So that's what I'm going to do. So let me begin with reviewing some of the basic features of the standard model. This is the picture you can keep in mind. So we have quarks. The pink particles over there are the three generations of quarks, first, second, and third generation. Then we have leptons, first, second, and third generation. And we have the force particles, the gauge forces, the Higgs boson, and the graviton is not here, but it should be here. It's a very important particle for cosmology, obviously. And so this is the particle. Now let me go into the details that I introduced last time. For the gauge group, the forces of the standard model are described by the symmetry SU3 cross SU2 cross U1. As we said, SU3 is just a complex rotations in three complex dimensions that preserve essentially the lengths and the angles between vectors. SU2 is the same thing in two dimensions, rotation in two complex dimensions that are length and angle preserving. And U1 is like real rotations in two dimensions. Okay? So this is called the strong, weak, and electromagnetic interactions that we introduced last time. There are three coupling strengths associated with U1, SU2, and SU3 that are called G1, G2, and G3. These are all numerically different at the low energies where we've measured them, and but not a lot. Like let's say around LHC energies, G1 is, let's call it a third. This is like a half, and this is order 1. So they are all order 1 numbers, but definitely different. And the so-called electromagnetic coupling that enters, for example, in the electric charge of the electron is just a combination of this G1 and G2, some particular combination of these two. So this is the gauge group that we introduced. Associated with SU3, there is particles that we are called the gluons. These are the force carriers of the SU3. The SU2 have W's and Z's, but it's called the weak gauge bosons. We'll mostly talk about W's. And the U1 has essentially the photons. In fact, the U1 and the SU2 contain linear combinations of the photon and the Z particles. So there is 8 gluons and 4 what are called electroweak gauge bosons. SU2 cross U1 is the electroweak group of Glashow, Weinberg, and Salam. So that is the nature of the non-gravitational forces in the Standard Model. And now let me write once more, just like I did last time, the representations of a single family to impress upon you how involved it is. So for example, there is quarks. There is what are called the up and the down, or the first generation up and down like quarks, which are called up and down, which are SU3 triplets, SU2 doublets, and have a certain hypercharge. So triplet means that it has 3 complex components, doublet 2 complex components, and hypercharge can be, in principle, any number. It can be irrational, it can be square root of pi, whatever you want. It turns out to be properly normalized to relative to the electron. It's a 6th. Then there is the antiquarks, the so-called up antiquark. Sometimes it's denoted by U bar, and sometimes by U conjugate. And it's an anti-triplet, which transforms with the Hermitian conjugate of the transformation under which the triplet transforms. And this has a hypercharge minus 2/3. Then there is the down antiquark, which is, again, an anti-triplet, which has different hypercharge. And then there is the leptons. These are all the quarks. Quarks are particles that carry strong interactions. And then there is the and the neutrino and the electron are a doublet of weak interactions, and they carry hypercharge of -1/2. So that's the representation. These are all fermions. There is also a scalar that is called the Higgs. So this is a scalar representation that turns out to have exactly the same quantum numbers of, so this is the famous Higgs. That was the last particle of the Standard Model to be discovered in 2012. So the Higgs has exactly the same quantum numbers, but it has different spin. The Higgs has spin 0. All the other particles, all the particles that I've written here have spin 1/2. And of course, the gauge bosons have spin 1. And finally, in at least what the minimal version of the Standard Model, there is a last particle, which is sometimes it's the positron, sometimes it's denoted by E plus or E bar or E conjugate, and it is a singlet under SU3 and SU2, and it has a hypercharge of +1. Okay, so those are the totality of the particles of the simplest version of the standard model. I keep saying simplest because, as you will see, you can add one more particle that is singlet under everything. There's no SQ3, no SQ2, and no U1 quantum numbers. And it turns out that we'll talk about it in a short while. It's called the right-handed neutrino. And it may well play a significant role for neutrino masses, which is a topic we don't have time to get into. So the thing that you gather from this is, even though it's amazing that the totality of, and of course there is 3 generations of these particles, so you have to multiply everything by 3, so, and that is depicted very clearly. So up and down can replace by charm and strange for the 2nd generation, or top and bottom, and similarly for leptons. Okay, so 3 times this. So even though, if you look at it sort of at face value, it looks fairly involved, it's still amazing that you can describe the totality of all experimental results ever made in terms of 3 copies of these families, a Higgs and these gauge forces and the graviton. So that's already pretty spectacular. I should say almost all. I'll come to the topic of dark matter later. And nevertheless, it seems, from the aesthetic point of view, it seems fairly contrived. In particular, I remember when I was a student, I found this especially contrived, not just the multiples, but these hypercharges look to be very funny. Somehow they tried very hard to be multiples of each other, and they have this weird fraction. So, in fact, when I was a student, I visited Stanford, I asked Lenny, I said, that standard model is too ugly. He said, you should read a paper by Georgia and Glashow, which was, of course, the original grand unified theory. And indeed, after looking at that paper, this choice of multiplets as well as the charges becomes very compelling. And that's what I want to share, this excitement of how elegantly these particles fit in a grand unified theory. And instead of the SU5 theory, I'll actually present a slightly bigger version of SU5, which is called the SO10 theory of grand unification. I'll do that in a few minutes, and you'll see how all of this begin to make sense. Okay, so now here, this is just to review. This is, again, the same transparency as before. This is just a brief summary of the things we discussed in more detail last 2 weeks ago. So you see the 3 generations. This shows much more information. It shows the charges and the masses. So you see, for example, the up quark is about 100,000 times lighter than the top quark. And of course, the neutrinos are far, far lighter than all the other particles by a factor of 1 billion. So you have, and there is a pattern that, if there is a pattern here, it's hiding extremely well. It seems, people have been thinking about these masses for several decades, and it seems like it's very hard to make sense of it. It may well be accidental, or it may well be related to something we discussed last time, to some anthropic or multiverse type selection, especially the particles that we are made out of, namely the electrons, the up quark and the down quark. They seem to have conspired and have just the right properties to allow atoms to form. And if you tweak a little bit the theory, all of a sudden you lose atoms, you lose atomic nuclei. You only have hydrogen, or you have no hydrogen, only heavy nuclei. So things are very sensitively dependent on parameters. So this suggests a potentiality for an anthropic or environmental explanation. I'm not going to go into this unless there is time towards the end. There may not be, the way I've planned out the talk. But that's all I want to tell you. We're not going to talk about the 20 parameters I was alluding to. For the most part, have to do with the masses of the quarks and the leptons. Of course, there are 3 so-called coupling constants, the G1, G2, and G3. So the totality of the 20 parameters is essentially embedded here. Okay, so together with the Higgs mass. etc. So now, now I want to march towards introducing grand unification. This is again a brief review of something I showed you last time. So these are this is, for example, how strong interaction acts on 3 quarks. So the up quark, for example, all quarks, but in particular the up quark, come in 3 colors, red, green, and blue. And the way strong interactions work, they essentially conserved all of these. Oh, this red, green, and blue, as we said, are just fancy names for attributes. Instead of calling them 1, 2, and 3, which is somehow a colder name, red, green, and blue feels somewhat more warm and familiar. So these are 3 attributes. You can call them redness, greenness, and blueness. And these 3 attributes are conserved, essentially conserved. So if you have a red quark become a green quark, it has to emit a red anti-green gluon, so that both redness and greenness are conserved. Right here, where 3 particles come together, it's called the vertex of the interaction. If you draw a little circle, you see that there is as much redness coming in as it comes out, and as much greenness coming in as it comes out. So redness and greenness and blueness are 2 attributes that are essentially conserved, but not quite. This S here, which I told you has to do with the volume preservation of rotations, of these rotations. This S stands for the following fact, that if you have red, green, and blue colors together, they sort of neutralize each other. They become a singlet, or they become a colorless object. For example, the protons and the neutrons are all colorless objects. They don't couple to gluons directly except through their constituents, so they are colorless objects. They don't carry bulk strong interactions. And so the exception is if you have red, green, and blue, it becomes neutral. It sort of washes out and becomes white, or neutral if you wish. And so in other words, if you have a red and a green, it acts as if it's anti-blue. It annihilates the blue. And in fact, this is a precise mathematical statement that if you put a red and a green together, you will get an anti-blue. And what I mean by anti-blue, I mean the 3rd component of the 3-bar representation of SU3 is called anti-blue. Just like the 3-dimensional representation 3rd component is called blue, the 3-dimensional representation of the anti-3, or 3-bar, or the conjugate 3, is called anti-blue. So red times blue is anti-green, blue times green is anti-red, etc. So and that's a very important property, which has to do with this letter S, and of course the number 3. So that's the overview of how strong interactions act on a given quark. Of course, they act similarly on all the quarks, and essentially similarly on all the antiquarks, which are just 3 bars. 3 bar and 3 behave completely in parallel. How about the electroweak interactions? Well, the electroweak interaction, for example, the U1 essentially acts like electromagnetism. So the electron remains an electron after it emits a photon. Okay, so it's not a change of attribute, it's some sort of counting. The photon is like a counter of the charge of the particle that it interacts with. SU2 is very similar to SU3. There are again 2 attributes. They are usually called up and down. So just to use the color analogy, the top I'll call purple and black, just to use colors for weak interactions. So again, blackness and purpleness are conserved. Same principle, except if you have 1 black and 1 purple color in a specific combination, they can neutralize each other. They can become SU2 neutral. So what's called an SU2 singlet. So it doesn't carry SU2 weak interactions. So that's how it works. Now, I will just now slowly, this is probably the next couple of transparencies are going to be completely new material, not a review of what not a brief summary of what I told you last time. So bear with me, I'll take a little time to introduce it. So here I'm introducing the concept of an SO10 spinner, okay? So it turns out it won't be clear from what I tell you that it has to do anything with 10-dimensional rotations because it's a strange representation of this group. So here is how to introduce it. First of all, 3-dimensional spinners. Well, we are somewhat familiar with 3-dimensional spinners. Spin up. The picture is spin up or spin down. So there are two states of a 3-dimensional spinner, up and down. And for the purpose of this discussion, instead of calling the two attributes up and down, I'll imagine that these up and down are sort of glasses of water or buckets. So you can have the glass full or empty. These are the two states. Up corresponds to full, down corresponds to empty. So that's the intuition we have about 3-dimensional spinner. It's a two-state system. Now, the 10-dimensional spinner of SO10 is just like, it's the same idea, except instead of having just one glass, which can be either full or empty, now you have 5 glasses, okay? And each glass has one of the attributes that we introduced, red, green, and blue. So these 3 attributes correspond to color. And associated anytime, let's say, the red glass is occupied, this signifies that the particle that it describes has red color red. And it also gets an attribute just by virtue, anytime this glass is full, you assign hypercharge minus a third to this box. If it's empty, of course, there is no hypercharge to assign. Similarly with green and blue, so these are, let's say, the color, the SU3 buckets. And these are the SU2 buckets. So there are 2 attributes, up and down, upness and downness, or purple and black that we introduced. And these represent the electroweak directions. And if the purple bucket is full, you assign hypercharge +1. If the black is full, you don't assign any hypercharge, 0. So this is the mechanics so far. And the rule that I told you as before to keep in mind that if the red, the green, and the blue, they are all 3 of them are occupied, it's like a singlet. It's like a colorless state. So if all 3 are occupied, it's like none of them is occupied as far as color is concerned. Not as far as hypercharge, but as far as color is concerned. In other words, again, red times green behaves like anti-blue. It annihilates the blue. Similarly for SU2, the same thing I was telling you before. If purple and black are both occupied, it's like there is no SU2 quantum number associated with it. So, okay, so that is, these are the rules that, there is one more rule. So now if you look at it, so there is 5 buckets or 5 glasses. And each glass can be in one of 2 states, full or empty. So there is 2 states to the 5th power. The total number of states is 2 times 2 times 2 times 2 times 2, which is 32. Okay? So this is the total number of states that, in principle, this describes. However, to construct the spinner, the so-called spinner of SO10, there is one more rule that only an even number of buckets has to be occupied. That's a rule. So instead of 32 states, you end up with only 16 states. Okay, so half of the states are eliminated because we have you forced to have only an even number of buckets. For example, here is one particle. Let's say the red spot is occupied and the purple is occupied. So this is a particle that carries color red, and it has the purple is occupied. So this means that it has weak interactions. So it's a triplet of color and doublet of weak interactions. And if you look at the hypercharge, it matches the right-hand, the up quark, the red up quark, okay? Red because the red spot is occupied, the red glass is full. And it's the up quark because purple is the up direction, okay? So it's a red up quark, that's what it is. And this same idea here, this is a red down quark because the down spot, the down glass is now full, not the up glass. So this is the down right. And of course, there is 3 of each. I could have made this quark green or blue. So there's 1, 2, 3 choices for up, 1, 2, 3 choices for down. Red, green, and blue colors for up and down. Okay, so times 3 stands for color multiplicity. So here is another particle. Now here are 2 boxes occupied again, the green and the blue. Remember, the green and the blue act as if they are anti-red. They annihilate the red. So this is like an anti-triplet representing an anti-quark. And if you work out the hyperchargers minus a third plus minus a third is minus 2/3, which is the hypercharge of the up anti-quark. Okay? So this is an anti-up anti-quark, so anti-red, I'm sorry. So this is the anti-red. And here is another. Now four buckets are occupied. So the green and the blue means that it's anti-red again. Purple and black are both occupied, so it means it doesn't have SU2 quantum numbers. But it has hypercharge. If you add up all the hypercharges, minus a third, plus 1, 0, you get plus a third, which is the hypercharge of a d bar. Now, here is another one. So this covers all quarks of a given generation, once you take the 3 colors into account. And of course, you also have 3 generations. So this pattern, again, repeats 3 times, once for each family. Now we go to particles that don't carry color. Okay, so here is one particle that has 3 colored boxes occupied. So this means it's color singlet. And it is, the black box is occupied. So it's a down-like entity that has no color. So it's the electron. You can work out the hypercharges, and it's the hypercharge of the electron. And similarly, here are 3 boxes occupied. So it's, again, doesn't carry color, this particle, but it's in the up direction. So this is the electron neutrino. So this is the doublet, this doublet here of neutrinos and electrons. And now the positron, interesting, it has no color boxes occupied, but both SU2 boxes are occupied. So it has plus 1, plus 0 hypercharge, so hypercharge plus 1. So it's this entity here, which has hypercharge plus 1 here. And again, there is 1 of this and 1 of this per generation. Finally, you have one new possibility that no box is occupied at all. And this is the state I was alluding to before. It's the right-handed neutrino. So the total number of states is 16. 15 are the states that I have indicated here, but there is one more state which has, it sounds a little boring. It has no SU2, no SU3, and no U1 quantum numbers. How could it possibly be interesting? Well, it could be, it turns out, if it exists, it's not sure that it exists. You can have neutrino masses without having this particle. But by far the most appealing theories of neutrino masses that can lead to at least some order of magnitude understanding of their masses is in theories where such a particle exists, and it's in fact super heavy. It can be 10 to the 12 times or 10 to the 14 times the mass of the proton. Nevertheless, it can affect physics at low energies. In fact, the heaviness of this right-handed neutrino can account for the lightness of the neutrinos as we know them. So that's a very beautiful theory called the Gell-Mann-Ramon-Slansky theory of neutrino masses, which was proposed back in '78. And anyway, it's one of the nice attributes of grand unified theories. Unfortunately, I don't have time to talk about it, but I just mention it. So these are all the particles of a given generation. They fit neatly into one single representation of O10, single representation. So instead of having 1, 2, 3, 4, 5, well, plus the right-handed neutrino if you need it, instead of having these 5 representations in the standard of the standard model, have a single representation which is constructed by these rules. So that is the beauty of O10, and of course, you can reproduce all of these attributes, including these weird hypercharges that I had found so annoying as a student. I don't think I was the only one, everybody. The moment you see this, you say, oh, maybe there is something deep with these grand unified theories. Now, yeah, and how about the gauge bosons? How do you visualize the gauge bosons? Now, the gauge bosons, remember from the picture I drew a few slides ago, the gauge bosons are associated with transitions. Let me go back to this picture I was showing here, for example. Gauge bosons are what is emitted when you transition from one quark to another quark here. The red quark becomes a green quark, and these gauge bosons are emitted to conserve color, okay, to make sure that redness and greenness are attributes that are preserved. Okay, so gauge bosons have to do with transitions from one quark to another, or from one particle to the other. So this suggests that we can visualize the gauge bosons as operations, or transitions are operations. Something happens. Okay, for example, if you empty the red bucket onto the green bucket, that's an operation. Okay, so if the red bucket is full, then you empty it on the green bucket, and so now the red becomes empty and the green becomes full. So this is like the transition I was showing you before of a red quark to a green quark. So this operation is mediated by the emission of the corresponding gauge boson, which and this transition to preserve color, the emitted gauge boson, as I said before, has to have redness and anti-greenness. So the two attributes cancel. So a red bucket empties onto a green bucket, and in the process you emit a red anti-green gauge boson. That's the process. That's how we visualize the gauge boson. This particular one is obviously the gluon. It turns a red quark into a green quark, just like the picture I showed you a minute ago. And of course, you have similarly red can go up to blue, etc. So all of these are the gluons. Now you can have another gauge boson that empties the purple bucket to the black bucket. So you start in a state where you have some purpleness, and then you empty the bucket to the black bucket, and you lose purpleness and you gain black. So it becomes the purple transitions to black, and in the process, you emit a red anti-black boson. So this corresponds to this picture I was showing here. Okay, black goes to, oh, well, I was showing the opposite. Black goes to purple with the emission of a black anti-purple boson, which is called the W boson. Okay. Now, so we've covered two of the bosons, the gluons and the SU2, the W bosons. There is a totally new category of bosons that is very interesting, which has to do with now mixing, taking one of the colored buckets and emptying it onto the SU2 buckets. Okay, so you can take this blue bucket and empty it onto a purple bucket. So this converts color to SU2 quantum numbers. This is pretty amazing. It's fairly unique. This means, for example, if you have a quark which has, let's say, some blueness in it, you can empty it to the purple, so you can lose the blueness, so you lose color. the SU3 or the strong force, and you convert it to something with just weak force or SU2 force, which could be a lepton, for example. So in these theories, not surprisingly, well, you can now mix quarks and leptons. Quarks can become leptons by emitting these new gauge bosons that are called the X bosons. Okay, so this, of course, leads to new phenomena. Just like in weak interactions are based on, this transition. A purple bucket empties into a black bucket, and it emits a W boson. This is how, the down quark or the up quark transitions to a down quark, or the down quark transitions to an up quark in beta decay when the neutron decays, or the neutrino transitions to electron. So these are new processes, the so-called weak interactions. So there is some new weak interactions that are associated with converting quarks to leptons. Now, such weak interactions sound very bizarre because we haven't experimentally seen transitions where quarks turn into leptons. In fact, there is also other interactions where two buckets can be filled at once. And these are called Y bosons in theories. So this is another type of transition where you can create something, let's say, with anti-green quantum number. Something that has no quantum number, let's say no color quantum number, you can fill two buckets at once and transition to anti-green. So these things amount to either converting quarks to leptons or quarks to antiquarks, as I will show you in a minute. So this is how you visualize.
Are there invisible buckets that you use to?
Yeah, no. Oh, here? No, because it's an even number, I don't have to specify where they come from. Yeah, so. Yeah. You can. This, you see, this means you can transition from, let's say, from this, these are 5 empty buckets. You can fill both the last 2 buckets at once by emitting this a boson which is called the Y boson. Okay, so you can convert a right-handed neutrino to a positron with these buckets. By the way, the Y bosons only occur in SO10, the X bosons, anyway, in SU5. But so these are the pictures of the gauge bosons. And now I want to discuss, essentially, take my timeline to discuss what are the physical processes that are associated with the gauge bosons that are new, in particular associated with these X bosons. And I will draw a couple of processes. Oh, okay, I lost. Okay. Okay, I guess. Can you hear me now? Oh, hi. Yes, this is. Oh, okay, that's what I was looking for. Okay, thanks. Okay, so let me in particular, let me just, it's simpler to illustrate it here. Let me go back to discuss what types of processes can be mediated by these X bosons. So take this, take this particle. So it has these 2 buckets full. It's called the right-handed up quark. And imagine what do you get when you take this blue bucket and you empty it onto this purple bucket. Okay? So you take the blue bucket and you empty it into the purple bucket. And what are you left with? Okay, so the initial state, I'll write the initial state. up bar red. Okay? Okay? So the initial state is this state up bar red, which has the green and the blue buckets full. Okay? Now imagine that you empty the blue to the bucket to the purple bucket. So you end up with something that looks like the top line, except instead of the red, the green bucket is full now. Okay? So you end up with up bar, up green. Okay? So if you empty the blue to a purple, you lose the blueness, gain purpleness, and you have green. The greenness is maintained. So you have a green up quark. So by empty the blue empty blue bucket into the purple bucket. So that was the operation. Okay? So that's the emission of in physical terms, up bar red becomes an up green by emitting a gauge boson which has which carries this blue to purple transition. Both it carries the quantum numbers blue anti-purple, if you want to attribute to it color and SU2. So that's what it does. Now consider so you have this gauge boson emitted. So blue to purple gauge boson emitted. Okay. Let's now, what does this gauge boson do? Okay. Now, remember we were considering blue to purple transitions. To see what this gauge boson, now the purple box is full. Now to consider what this gauge boson does, look at this line. This is this line and that line have something in common. They have the blue full and the purple empty. Blue full and purple empty. So let's see what happens when this blue transitions into purple. Okay, this particle here is the electron. So in the same process, when you empty blue to purple, what is emitted, both processes are the same. You empty blue to purple, so a gauge boson is emitted with these quantum numbers. What do you get when an electron is emitted, when the blue goes to purple? Well, you get a particle, so you lose the blue, you gain the purple. Here is a multiplet. Where is a multiplet? Okay. So this becomes a red and a green is an anti-blue. Okay? Red and green is anti-blue because you lose the blueness. And it looks just like this, except instead of the red spot being occupied, the red and the green being occupied, the green and the blue are occupied. So you go from here to here. You go from an electron to a down antiquark, which is anti-blue. Okay? If you just down anti-blue. Okay? So the bar means antiquark, so it carries anti-blue. So that's the process. Okay? So when you empty a blue bucket into a purple bucket, you transition, you can cause two transitions. One is that the up bar red becomes up green. The other is that the electron can become a down bar blue. Okay? Now, imagine now you want a process where there is no X boson in the final state. So the X boson first has to be emitted, and then it has to be absorbed. So when it is emitted, when the X boson is emitted, okay. Maybe I should put it here. Okay. So when the X boson is emitted, you go from left to right, as I have been discussing. So now you have an X boson that has been emitted. So I'll draw the line. So U bar, I won't keep track of colors in detail because it will take me too much time. So you start with a U bar red. You emit a boson that has these blue anti-purple attributes, and you end up with U green. Okay, so U bar red becomes U green. Now you want this to be absorbed. Okay? Now when you absorb it, you have to go backwards. Okay? So, for example, and you can do that. This means you go from D bar to electron. So here is a D bar blue, goes to an electron. Okay? When the X boson is absorbed. So when it's emitted, U bar red becomes U green. When it's absorbed, D bar blue becomes electron. So, and as I said before, you want the X to be emitted and absorbed because you don't want the X particles in the initial and the final state. They, as we will see, they are very, very heavy particles, so you can't easily produce them in the lab. They can mediate forces, they can mediate processes at some rate, but they are very, very heavy. You can't produce them what's called on shell as physical particles. So that's a very strange process. You have two antiquarks, and the two antiquarks turn into a quark and a lepton. And to see how strange this is, let's tag onto this process. Let's say have a spectator particle, something that doesn't participate in any interactions. Let's have a spectator up bar, red, blue, green. Okay, so the initial state has up bar green, up bar red, down bar blue. And the final state, the up bar green continues. Okay, so the initial state has three. So time runs vertically now in my picture. Think of time running vertically, so early, late. So in early times, you have let's say, a state of two up antiquarks and a down antiquark. This is a particle that is called the antiproton. It's called P bar, antiproton. It's just like a proton, but it's the antiparticle of a proton. Okay, the antiproton, which normally is a stable by itself. If you have it in isolation, it's stable, just like it's the antiparticle of the proton. Just like the proton is stable, this is a stable particle normally. So the antiproton can become, which has charge -1, by the way. The proton has charge +1, the antiproton -1, can become an electron and a bound state of up quark and up antiquark, which is called, typically, if you have a quark and antiquark in the final state, they form a bound state, at least at lower, that is called pion. It's called a pion, pi 0. That's the fancy name of it, pion. It's just a bound state of a quark and an antiquark. It's an unstable particle again. It decays to 2 photons. But so an antiproton, which is normally stable, therefore, becomes a pi naught plus an electron. Or if you take the conjugate of this means the protons that are in our bodies this very minute can decay into a pion and a positron. Okay? So this is a spectacular prediction. It says that in grand unified theories, because of these transitions that involve these color quantum numbers converting to weak quantum numbers, you can have protons being unstable by the process that I just drew here. Protons can become electron and pi 0. Pi 0, for example, can decay to 2 photons. So in the final state, in the end, the proton will go into 2 photons and a positron. Okay? So this is an astonishing prediction made, I guess, around 74. It says that matter as we know it, nuclei inside our bodies are unstable. So matter is not stable, atoms are not stable, etc. Now, this prediction, let me continue here. Of course, in practice, we know that the proton is an extremely stable particle. It has been around for much longer than the age of the universe. When a proton decays, let's say, goes to pi 0 plus positron. It can also go to a photon, by the way, plus a positron. But let's stick with this. Eventually, you can get, for example, from pi 0, a photon plus a positron.
How can a proton be around for longer than the age of light?
Yes, I'm coming to this. Yes. So the proton decays. The energy would be released would be enormous, and we would know about it even if its lifetime is long. What are the limits to the lifetime? To come back to Lenny's question, clearly the universe is 10 billion years old, and definitely protons have been around much longer than that. In fact, there is a famous physicist called Goldhaber, Maurice, I guess, Goldhaber, who first sort of estimated based on the amount of energy release in this reaction, which is huge. You know, the proton mass is, 1 GeV, the full energy, 1 billion electron volts. So effectively, the final states are, very light. So you have a lot of energy, 1 billion electron volts worth of energy in one process. So it can cause a lot of damage, such a large amount of energy injected. Goldhaber guesstimated that just from the very fact that we don't get cancer from such proton decays, the lifetime must be longer than about 10 to the 17 years, which is 10 million times longer than the age of the universe. Of course, physically, you can get much, by doing dedicated experiments, you can get much better limits on the lifetime of the proton. So today, the best limits is a few times 10 to the 33 years.
So, Savas, you don't mean that the proton has been around for more than the age of the universe. You mean it will be around?
It will be, yes. 10 to the 23 times the age of the universe. It will be around that long before it decays, okay? 10 to the 23 times the age of the universe. This is the proton decays have not been seen, okay? So this is only a limit. The lifetime of the proton has to be longer than 10 to the 33 years. In fact, it's almost 10 to the 34 now. Okay, it's an amazingly long distance. How do they know about it? Oh, this is an amazing story, so I'll show you. I'll come back to this in a moment. Okay, so here is the way they know the best measurement of the proton lifetime is shown here. There are two ways to measure the proton lifetime. One is take a single proton and wait for 10 to 33 years. The other is take 10 to 33 protons and wait for order a year or so. And they did the latter. And that is why it's a very big experiment. This is called super Kamiokande. So what you see here, this is like a cylinder whose diameter is 40 meters and is 40 meters high. It's a huge cylinder, so that's what 40 meters. And it's what it has inside is exceedingly pure water. The water is so pure that the light that can be produced can travel essentially from one end to the other. Anyway, there are pretty amazing numbers. Normally light would travel just a few meters, but now it travels 40 meters because it's a very purified water. And what you see, these things are a few thousand photomultipliers that sort of surround the whole thing. What you see in the depth over there is just a little boat that goes around to, I guess, to fix photomultipliers. Where is, here. So that's the Super Kamiokande. This is like a third generation experiment. This is like 50,000 tons of water. It's a huge amount of water. Of course, this experiment did not yet see proton decay. And there are planned upgrades to this. This is an ongoing project. The experiment is still running. They didn't discover proton decay, but just an amusing historic note, they discovered something else, which got them the Nobel Prize this year. In fact, they discovered an aspect of neutrino physics, which is neutrino oscillations. So there are some, as I'm sure you know, the universe is full of very high energy cosmic rays, what's called cosmic radiation. So it turns out cosmic rays can interact with the atmosphere. As they come down with high energy into the atmosphere, they collide with atmospheric particles and produce a mu neutrino, the neutrino that goes with the muon. Okay, they do it in the atmosphere above the detector. They also do it on the other side of the Earth, okay? Now there is several tens of kilometers of atmosphere here, but here the neutrinos have to travel much longer. They have to travel through the 6,000 kilometer radius of the Earth. And what they found is that they have more mu neutrinos that are coming from the top than the bottom. And the interpretation is that the nu mu, the mu neutrino, turns into a tau neutrino. And that, together with the Nobel Prize for this year, was to this experiment, and also to another one in Canada, which is called the Sudbury, or the Solar Neutrino Observatory, which studied other aspects that sort of confirm that this is nu mu to nu tau transition. But anyway, this is an amazing phenomenon that very often happens in science. You pursue something, and you discover something else that sometimes is more important. Sometimes, I mean, in this case, I would still think proton decay would be more important, but this is pretty great physics that they discovered by just having these detectors. This huge amount of water that they have is ideal. It's exactly what's needed to detect neutrinos, because neutrinos are so weakly interacting that you need a lot of matter to give it a lot of chance to interact with many different atoms. So in fact, the story, I was tempted to mention another such serendipity story, which is the story of supernova 1987A, the earlier generation of Kamiokande, not the Super Kamiokande, but the earlier generation that was around in the 80s, was also much smaller. That was like 3,000-ton detector. They also were, early in the 80s, there was a lot of excitement to test grand unified theories. So they built these detectors, well, one in Japan, and there were several of them. There was one in the US by Illinois, Michigan, and Brookhaven, the IMB collaboration. So they were all looking for proton decays. And they turned on, like in the mid-80s, to look for proton decays. And lo and behold, in 1987, February 26th of 87, they see a supernova explosion. So that's the supernova 1987A, which is, it hadn't happened that close in the last 350 or 400 years. So we were blessed with this. They measured a total of about 23 well, 3 different experiments, measured 23 events, 11 of them in Kamiokande. And anyway, these events have been studied to death. They span, the first and the last event are separated by 13 seconds. And anyway, that ties into beautifully to what people expect from neutrino physics when you have a supernova collapse. So that's another case of, serendipity. That, I mean, if Georgia and Glashow hadn't built their grand unified theory, probably people wouldn't have bothered to build these proton decay detectors, at least not that early, and they would have missed the 1987. They got it within a few years, like a couple of years. I forget the time scale, because there were 3 experiments that saw the neutrinos. So it was great luck. If you think, a year or 2 out of 400, which took from the previous supernova, it was quite lucky. Okay, so this is how we know the lifetime, 10 to 33 years. As I said, a lot of resources is going to increase it. It is somewhat, now I will talk a little bit about theoretical expectations. This is a big number. What does it correspond to in terms of elementary particles? Turns out that the proton lifetime, so proton lifetime, scales is proportional to the inverse 4th power of the mass of this X boson, the X boson that causes transition between the colored and the weak directions, to the 4th power. So it's quite sensitive. If you are off by a factor of 2 in the prediction, your expectation of the X boson mass, then the lifetime is off by a factor of 16. Now, so a factor of 16 is nothing for the theory, but it's a huge deal for experiment to multiply by a factor of 16 these already enormous experiments is a non-trivial challenge. So the question is, what are the theoretical expectations for the masses of these X bosons? And that's what I want to spend a few minutes discussing now. Okay. So So that's the topic I want to discuss. Okay, so what's the theoretical significance of the masses of these X bosons? Now, as I was saying before, these X bosons are very important because they link 2 aspects of the standard model physics that are ordinarily not linked. I have it. Namely, the weak directions, the color direction, okay, this blue turning to a purple, a colored direction turns into an SU2 direction. So strong and weak interactions mix with each other, or quarks can turn into lepton, colored objects into uncolored objects. And it's not surprising that such transitions happen in grand unified theories. After all, grand unified theories unify quarks and leptons into one big, what's called multiplet, one big representation. This means that they are, as far as the fundamental theory is concerned, they are not different particles in quotes. What does this mean? These 16 entities that fit inside this spinor of SO10 that I showed you shouldn't be, in the very fundamental theory, should be treated as one and the same entity. These 16, just like an electron with spin up and an electron with spin down, we don't tend to think of them as different particles. Physics at very short distances shouldn't be able to tell the difference between quarks and leptons if this idea of grand unification is valid. Same reason, it's always the same with symmetry. An electron here, an electron there, you don't think of it as, well, it's a different, it's the same particle, has the same properties as you move it from here to here, to here. Its mass and charge and spin haven't changed. So that's because of translational symmetry. So when you have symmetries, you are asked to identify things, objects that are connected to each other by a symmetry operation. So similarly here, if you have a SO10 symmetry, you shouldn't be able to tell the difference between any one of these 16 entities, at least at very short distances. And now why do I keep insisting at very short distances? Because clearly these bosons have to be very heavy. If you work out from the experimental constraint the mass of these X bosons, they turn out to be approximately a few times 10 to the 16 times the proton mass. Very heavy. I remember the Large Hadron Collider is like 10 to the 4. So LHC is like 10 to the 4 times the proton mass. MC squared, if you wish. Okay? So it's way, way above any energies that we can directly probe in accelerators. This X boson, which causes transitions between quarks and leptons, which has to be part of the game, part of the symmetry, because the very idea of having all these 16 entities be identified as one is to have transitions between them. So these bosons are very, very heavy. This means that unification is not something we expect to see at low energies. We will, if we are lucky, we'll recover it at very high energies. We'll only see it at very high energy. So how does this work? So I'll make a famous plot of strength of coupling the vertical axis is the strength of coupling. And the horizontal axis will be the energy. It'll really be, this will be a log of energy. But okay? So this, for example, is somewhere out here. So this is, let's say, LHC energies are somewhere here. Large Hadron Collider, 10 to the 4 GeV. And somewhere out here is the Planck mass that I haven't really defined. It's the scale where gravity becomes strong. It's just 10 to the 19 GeV, very high energy. Okay, and so this is the energy scale. This is called the energy desert because some people don't expect much to reside between here and there. And we do experiments here. Let's say we do experiments here and we measure the strengths. Let's say the strong interaction is here. Strong is the strongest, so it's the highest strong. This is, let's say, electromagnetic, and this is weak. This is cartoon. So we measure, so this is like maybe a third, this is like a half, this is like 1. So they are all the same. So they are all different. They are same order of magnitude, but different numerical detailed numbers. So it's quite clear that if unification is a correct idea, it's not valid at low energies. If it was, these three couplings would be the same. Okay, so they are not the same. So how does this unification manifest itself? The way it manifests itself potentially is the following. The strong interactions start out the strongest, but it turns out they get weaker as you go up in energy. And the weak and electromagnetic, well, actually, so they sort of, all three of them tend to converge the weakest tends to get stronger, the one in the middle gets a little bit stronger, and they all have the tendency to converge, okay? Now, how do you extrapolate from low energies to high energies the values of these couplings? Now, remember, normally these are called coupling constants, which means that, oh, well, if they are coupling constant, they must be constant. In particular, they should be constant as the functions of energy. This is true approximately, and it's true in classical concepts, classical physics. But in quantum mechanics, these quantities are not exactly constant. They depend on the logarithm of energy. So because they depend on the logarithm of energy, and this logarithmic dependence has a small coefficient in front, they evolve slowly. So they converge, even though they tend to increase, the weak tend to increase and the strong tend to decrease, so they converge. They converge very, very slowly. So you can ask the following question. Imagine that the standard model is valid from LHC energies all the way to some very big energy scale, like the Planck mass. What happens to these coupling constants? Well, they converge happily for a while, and they almost meet. I don't quite know how to draw the picture. They sort of miss by order 25% to, in other words, two of them, I forget which two, I think two of them meet first and the third one intersects later. So they sort of miss, but they don't miss by a hell of a lot. Now, 25% turns out to be hugely significant from the point of view of experimental precision. These things we know very well. They've been, in fact, measured by a lepton collider called LEP, also at CERN. Very precisely, these couplings. And we know how to extrapolate them. If we assume that we know all the physics between here and there to be, let's say, the standard model, we can extrapolate them. We could get a picture where two of them meet first and the third one, well, whatever. These two meet first and they miss. And qualitatively, it's okay, but quantitatively, they miss by a significant amount. So this is the story for the standard model. It turns out, and I doubt I'll have, even though I'm sort of ready to talk about supersymmetry, I'm not sure I'll have enough time to do justice to it. All I want to tell you is the following. If you assume that at the Large Hadron Collider, we discover a new symmetry called supersymmetry, which means that for every particle that we know, there is a corresponding partner that has different spin. And so if there is supersymmetry around this energy, and you extrapolate these couplings, you find out that they meet two very significant. You find out a picture like this, that strong, weak, and electromagnetic interact, converge, and they intersect at the same point. Again, how important this is? Well, this is at the order of 2 to 3%. They converge at the same point. If you have supersymmetric particles between the LHC energies and here. Since we have not seen supersymmetry, at least not yet at the LHC, we cannot claim that this is an amazing success. It's in fact the other way around. This was tested when LEP and SLC turned on around 1990. So by 91, the initial values of the strong electromagnetic and weak interactions were measured to high enough precision to know that if you extrapolate them with the supersymmetric particle content, they meet. So this was considered one of the big pieces of evidence that we should see supersymmetric particles at the LHC. And we may still discover them. The LHC turned on at 13 TeV and will be running for the next 3 to 4 years at this energy. So there is a chance that we'll discover superparticles, and then this picture would neatly, converge. So this is one of the most precise tests of physics beyond the standard model. It seems to suggest that there is supersymmetry somewhere around LHC energies. Now, as I told you, because the coupling constants depend logarithmically of energy, I cannot really pinpoint whether it's at 100 GeV or 1,000 GeV or 10,000 or 100,000. Because it's a log multiplied by a small number, the theory is not precise enough to tell you exactly what energy, how high the energy at which supersymmetric particles have to appear is. On the other hand, qualitatively, we expect some action to happen here, hopefully within LHC. So this is, so if you take this value to see where this coupling constant meet, you find a mass which is in fact in this range, few times 10 to the 16 times the proton mass. So we could get lucky and see proton decay in the next upgrade, but as I told you, if you are off by a factor of 2, which is very easy to be off by a factor of 2 if you logarithmically extrapolate what we know from high energies, then you can be off by a factor of 16 in the rate, which is hugely important for experiment. It's also fair to say that it's hard to build theories where the lifetime is much longer than 10 to the 33, 34. In fact, there is a whole story I'm not going to get into. There are contributions to the proton lifetime that scale as the square of the mass of this grand unification mass. It depends, the square because it depends on the mass of a fermion, the fermionic, anyway, the fermion, a fermion called the colored Higgsino. And there you typically get much faster lifetimes, by a factor of 10 or 100 faster lifetimes than this. And in fact, you have to push the theory to get the lifetime to be so long. So that you can take either as evidence. If you're pessimistic, you say, oh, well, the fact that we haven't seen proton decay is against, or you can be optimistic and say, oh my God, in most theories, protons should have already decayed. So surely the next upgrade will see the proton decay in a supersymmetric fashion. I should say, by the way, this picture that I drew is fairly accurate. Unification in non-supersymmetric theories turns out to happen relatively early at mass scales of 10 to the 14 GeV. In supersymmetry, it moves to 10 to the 16. And that's a good thing because it would be hard to justify, this lifetime would have been seen. This was the sort of lifetime in the 80s that people were aiming for in standard grand unified theories without supersymmetry. Supersymmetry moved us out here. So that's something to expect. Now, so that's one of the good stories. I didn't tell you the most important qualitative success of grand unified theories, which is the question I posed last lecture, which is why are atoms neutral? Okay, so for example, if you take hydrogen atom, okay, if hydrogen atom has an electron, so here is the electron, it has a proton, and the proton has 3 quarks, 2 up quarks and a down quark. So the up quark has charge plus 2/3 times the electron charge, 2/3 times the electron charge, plus 2/3 times the electron charge, and the down quark has minus 1/3 times the electron charge. Plus 2/3 minus 1/3 gives you plus 1, and the electron is minus 1 times the electron charge is negative. So the total, the atoms are neutral as a result. And this is hugely important. For example, if this failed to be the case, even to a precision of 1 part in 10 to the 19, then then let's say the atom, the hydrogen atom, has a charge which is, instead of being 1, instead of being 0, it's 10 to the minus 19 times the electron charge. Okay, in that case, the gravitational force between 2 hydrogen atoms would begin getting overwhelmed, would be balanced by the electrical repulsion of two hydrogen atoms. And simply because the electrical force is intrinsically so much stronger, even if you have a charge excess of 1 part 10 to 19, you compete with gravity. So the world would be a very different place if atoms were not. Turns out the best limits are for the electrical neutrality of atoms is that they have charge less than 10 to the minus 22 or 23 times the electron charge, 22 or 23. There is a proposed experiment that can be done using atom interferometry, which can take this number down several orders of magnitude. Maybe, this is the most optimistic, 10 to the minus 30. 28 for sure, maybe 10 to the minus 30, using a 10-meter atom interferometer that is in Mark Kasevich's laboratory on the basement of Varian building. So, but this is where it stands now. It's a very fascinating experiment. Essentially, anyway, I don't want to come into it. You take a gas and you apply some rapidly oscillating voltage, and if there was a net charge, the atoms would oscillate, would create a sound wave. So you actually put, you listen for electric charge oscillations. And if someone had told me that you can get that precise with a very primitive experiment, you have a speaker that tries to pick up the vibrations of the atoms from, I wouldn't have thought so, but that's how good the experiment. This is the best experiment today for the electrical neutrality of atoms. 10 to the minus 19, anybody can get by what I told you. 10 to the minus 19 is also the ratio of the proton mass to the Planck mass. So this ratio measures the gravitational force of a hydrogen atom on itself, let's say. Okay? So this is 10 to the minus 19, and it's attractive. If there was a net charge excess of 10 to the minus 19, it would be the same strength and repulsive. So the 1 part in 10 to the 19, you can get easily to get down to this. It becomes challenging. So this is, so now the theory. So that's the motivation. This begs for an explanation. Charge quantization. Oh, this is called charge quantization. It's the statement that why is it called charge quantization? The electric neutrality of a hydrogen is called charge quantization because it is exceedingly important that the down quark charge is exactly to 23 decimals a third, and that the up is exactly 2/3, 23 decimals. 2/3 times the electron charge. So this ratio of 2/3 to minus a third to 1 has to be to a very high precision, to 23 decimal. In the standard model, because the theory has a cross U1, remember I explained that the difference between SU3, let me go back here. I explained last time that one of the big differences between the gauge group SU3 and SU2 on one hand and the U1 on the other is that in U1 you can have any arbitrary charges. The charge can be square root of 2, pi over e, or whatever, any multiple of some fundamental charge. For SU3 and SU2 on the other hand, there is you cannot have a multiplet that is, let's say, between a scalar. Scalar is something that does not transform under SU3, and a triplet of SU3. So there is scalar, which has one component, and a triplet has 3 components, just like here. There is nothing in between. There is no representation between a scalar and a triplet with 2.5 particles or 1.5 or anything in between. They're just like as we were discussing last time. Angular momentum is quantized in some units. The algebra of angular momentum and the algebra of SU3 force you to have just a discrete set of possibilities, still infinite. You can have many, many multiplets, many different representations, but there is nothing in between. There is the smallest, the next one, and the next one, etc. So because of that, if you manage to embed SU3, SU2, and U1 into a grand unified group, like I was doing with SO10, then you have automatically explained why the charges that appear in the theory are quantized, because SU3, SU2, and U1 are eventually embedded into a grand unified group, which becomes, they are described at this very high energy that I'm denoting here. They all become one coupling. There is no G3, G2, G1. If you go to very high energies or very short distances, there is just one coupling. There is this called the SO10 coupling, just one number. And the SO10 has an algebra similar to the algebra of angular momentum. It's what's called a non-abelian group. So all the charges are quantized, so including the U1 charge. So charge quantization is an important qualitative success of grand unified theories. Yes. Let me see what, it's 8:30. Yeah, the next topic, there is clearly the standard model. Beyond the standard model is an enormously developed field, so there are many topics that I could talk about that I didn't talk about. I only have, it goes for 9. I can tell you a few things. Yeah, let me begin telling you a few things about, let me go past this. Okay. This I showed last time. Let me go past this. Let me, now, even though time is short, I will try to tell you a few things about supersymmetry, which I have mentioned, and it's the most appealing possibility for physics beyond the standard model that can be seen at the Large Hadron Collider. So let me begin with the motivation for supersymmetry and just a few aspects of it. So as we discussed last time, the hierarchy problem can be phrased in some equivalent the different ways. There are many facets to the hierarchy problem. One way is to say, why is gravity so much weaker than, let's say, electricity or all the other forces of nature? Another way that's more fruitful in some ways is to define the following two mass scales. There are two fundamental scales in the standard model. One is the Planck mass. The Planck mass is the scale at which gravity becomes strong. So if you take two particles of mass m, and you ask when is their force becoming large, okay, in a way I'll define in a moment. So the force between them is g Newton times m divided by r squared. R is their distance. Okay. So, and it's attractive. So when does this force? When the numerator here becomes of order 1, then gravity becomes strong. If the numerator becomes of order 1 divided by 137, then gravity becomes as strong as electricity. And for electricity, the corresponding quantity here in the circle is 1 divided by 137, let's say for 2 electrons. If this quantity becomes 1, then gravity becomes strong. And then the mass, this mass is called by definition, it's called the Planck mass definition. So m Planck is given by the formula I have there, 1 divided by the square root of g Newton. So that's when gravity becomes large, that's the definition. Okay. So, so one scale is M-Planck. The other scale is the weak interaction scale, which can be similarly, it characterizes the strength of ordinary weak interactions. For example, radioactivity, what's called beta decay. And that is only 1,000 GeV, which is the same as the LHC energies. It's in fact a tenth of the present LHC energy. So these are the two important scales in the Standard Model, and the hierarchy problem can be phrased as the distance between the enormity of the separation between the gravitational scale and the weak scale, the weak interaction scale, mass scale. And so there are two aspects to the hierarchy problem. One is the question, how come these two numbers are 16 orders of magnitude different? So that clearly seems to beg for an explanation. The second issue is that even if you imagine setting this ratio at when you define the theory at the Lagrangian, when you write down the Hamiltonian or the Lagrangian of the theory, you just put these numbers in by hand. One is 10 to the 16 times bigger than the other. When you compute quantum corrections, quantum mechanical corrections to the theory, they tend to pull the two scales together. The heavy physics that is involved at the Planck scale pulls up all the weak interaction physics up to the Planck scale. So this is called the stability problem, that the hierarchy is not stable. The separation between the gravitational and the weak scale is not stable under quantum corrections. And in terms technically, the way this is supposed to be a diagram that attempts to clarify this. So for this purpose, imagine for a moment that time runs horizontally. Okay, so time. So here is a Higgs particle. This is a scalar that defines the weak interaction scale. The magnitude of the Higgs particle, or the Higgs field as it is called, defines the weak interaction scale, defines the G Fermi, or the mass of the W bosons. So imagine a Higgs particle moving in time. Then, according to Heisenberg's uncertainty principle, the vacuum is not empty. It's full of virtual pairs of particles. Here is a top anti-top pair that can be created and then annihilated spontaneously. It can appear. It appears at this moment of time, disappears at this moment of time. And then again, appears, disappears, appears, disappears everywhere in space. If you look at short enough distances, and now we're talking 10 to the minus 18 centimeters or smaller, much smaller than the distance of than the size of an atomic nucleus, the vacuum is full of pairs of particles. It has electrons and positrons, muons, all the particles, top, anti-top. So they come and go because the uncertainty principle allows them to come and go without violating energy conservation. So they come and go for a very short amount of time. And their presence affects the properties of what's around them. And this, of course, is this effect on the properties of matter due to these quantum loops, these pairs of particles that populate the vacuum, is something that has been experimentally confirmed. If you measure energy levels of the hydrogen atom, you can see effects of these virtual pairs of particles. They are not just in our minds, little pictures. They cause what's called a polarized vacuum. You have an electron-positron pair. It's like having a little dipole, positive and negative charge. Appears and disappears, appears, disappears. And little dipoles of positive and negative charge can affect the electric force between two particles because they can partly screen. If you have a positive and a negative charge in the middle between two big charges, the force between the big charges can be screened by the presence of these virtual entities. So these these particles are known to have effects on the physics. The famous lamp shift that has been computed by theorists in 1948, Feynman, Dyson, Schwinger, Tomonaga, the people who computed this, got a number to 10 decimals, and experiments by Willis Lamb and collaborators confirmed their computation experimentally by measuring the energy levels of hydrogen atoms very precisely. So these are real effects. For the case of the Higgs, they are also undesirable because it turns out that these virtual processes that involve, let's say, top quarks can shift the mass of the Higgs all the way up to the Planck scale. Essentially because you can have top quarks appear and disappear at arbitrarily short time intervals. And the shorter the time interval, the higher the energy scale that is being probed by these processes. So the Higgs particle in the standard model would be expected to be at the Planck scale, and that's highly undesirable. This means weak interactions would be as weak as gravitation. So in order to avoid this, we have to do what is called tune parameters. Effectively, we have to take the result of this quantum mechanical computation and subtract a number that's almost equal to it to a precision of 32 decimals. Okay, so you take a big quantum correction, you subtract from it an equally big classical thing that you put in by fiat by hand, and you tune it to 32 decimals to make sure that the Higgs mass is light, because the Higgs mass defines the weak interaction scale, which is 16 orders of magnitude below the Planck mass. So this is this way of phrasing the problem is the famous fine-tuning problem. To avoid this, one way to avoid this is to postulate that there is a new symmetry that protects the Higgs from such corrections. Now, this symmetry, such symmetries, amusingly enough, also play a role for electrons. In the end of the 19th century, a couple of physicists called Abraham and Lorentz, I'm sorry, I guess this is the famous Lorentz, worried about what was then called the self-energy of the electron. Well, it was called self-energy a bit afterwards. So the idea is the following. If you take the electron, it has an electric field around it. And the electric field goes like 1 over r squared, which means as you go to shorter and shorter distances, the electric field becomes bigger and bigger. And because the electron is believed to be a point particle, you can take that formula classically at arbitrarily short distances and get a bigger and bigger electric field. Now, when you have such a large electric field, it carries a lot of energy. You may be familiar that the electric field carries energy density associated with it that is proportional to the square of the electric field. So if you take the total amount of energy that is contained in just the electric field of the electron, you find that it's divergent. It turns out to be linearly divergent. Divergence like 1 over the shortest possible distance that you can imagine going to the electron, which, well, in principle is 0. You can imagine going all the way to the point where the electron is. But if you somehow cut it off at the Planck length, say, well, we don't know the short distance physics at distances that correspond to the inverse Planck mass, which is Planck length, 10 to the minus 33 centimeters, you get a number where the energy in the electric field of the electron should be proportional to the Planck mass times the fine structure constant. So this is now, we know that energy is mass, so this energy would contribute to the mass of the electron. Anytime you move an electron, this whole energy would have to move with it, and that would manifest itself as inertia for the electron. This would mean that the electron mass, instead of being 1,000th of the proton mass, would be 10 to the plus 19 times the proton mass. So that was an outstanding problem in the late 19th century. I don't know how. Then, and the problem continues. Of course, then quantum mechanics came, but it continues in non-relativistic quantum mechanics. You know, without relativity, you have a similar diagram that again, this is like the diagram I was showing for the Higgs. This is a virtual process where the vacuum an electron can convert to another electron and a photon, for a short amount of time, and then back to an electron. This shifts the energy, the mass of the electron, and it's also this also gives you what's called a linear divergence, a correction proportional to the first power of the Planck mass. The situation completely changes when you go to quantum mechanics. In quantum mechanics, because of the quantum mechanics, the relativistic quantum mechanics of Dirac, introduces some new particle. In addition to the electron, you have a new particle called the positron, which is forced upon you by relativity. And so instead of the electron having just two components, electron with spin up, electron with spin down, which is what happens in non-relativistic quantum mechanics, where rotations is your symmetry, ordinary rotations in space. When you go to Lorentz transformations, rotations in space-time, you're forced to introduce also the positron. So there is electrons with spin up and down and positrons with spin ups and down. And the positron has to have the same mass as the electron, again, because of Lorentz invariance. And the positron turns out to be exactly what you need to cancel this enormous correction to the Planck mass. So graphically, or in terms of diagrams, the corrections to the mass of the electron that comes from such diagrams are canceled precisely, the dominant terms are precisely canceled by diagrams where the electron goes backwards in time, and therefore it manifests itself as a positron. And this cancellation, it's not like an accident. It is a consequence of Lorentz invariance. In fact, Lorentz invariance implies a symmetry that's called chiral symmetry that acts on fermions. And that consequence of Lorentz invariance is responsible for why the corrections to the electron mass cannot have any they cannot be big, cannot be proportional to some arbitrarily big scale like the Planck mass. They have to be to the original mass of the electron. So if your input mass to the electron in the theory, the starting mass that you put in your Hamiltonian, in your Lagrangian that defines the theory, is ME, then the corrections are at this number alpha, which is 1 over 137, times the mass of the electron, times some logarithm. So the corrections to the electron mass are under control. In particular, as the mass of the electron goes to 0, the corrections go to 0, because there emerges a new symmetry, which is a consequence of this Lorentz symmetry, which is chiral symmetry. Okay? So you see, what I told you so far does not explain why by itself why the electron mass is smaller than the Planck mass, but it tells you that if your input mass is smaller, quantum effects are not going to raise the mass all the way up to the Planck mass. A small mass will get small corrections, okay? And that are very insensitive, are only logarithmically sensitive to short distance physics. This M Planck is high energy or short distance physics. So that is the lesson we learned. This is from about 100 years ago, from quantum field theory 90 years ago, about how symmetries can protect particles from getting very big corrections to their masses. In this case, it's Lorentz invariance or chiral symmetry that forces this to happen. Supersymmetry is nothing but one using this idea to protect the Higgs. Notice that the crucial point that I didn't elaborate here too much, the crucial point turns out to be that the electron is a fermion, okay, that it has spin 1/2, And because it has spin 1/2, it allows it to possess either an exact or an approximate chiral symmetry, which is a consequence of this Lorentz invariant theory of the electron. So this can happen for spin 1/2 particles. It does not happen for spin 0 particles like the Higgs. And the idea of supersymmetry is to build a theory where scalars like the Higgs and fermions are related to each other. Somehow, these are new rotations, very strange rotations, which can convert a boson, like a scalar, to a fermion. Okay? So it's instead of having ordinary rotations where the x-axis can become y-axis, okay? You have rotations where a direction which is scalar becomes a direction which is fermionic. So this means that a scalar and a fermion are connected. Their properties are connected. Just like the properties of the x and the y-axis are the same, it's just a label. In supersymmetric theories, the properties of scalars and fermions are connected. They are related to each other. And if you have an exactly supersymmetric theory, the particles always come in pairs of scalars. Scalars come always with friends, with fermionic, what are called superpartners, partners. And if supersymmetry is exact, the mass of the fermion and the mass of the scalar have to be exactly the same. Okay, so for example, if this scalar that I denoted here by phi is the Higgs particle, there will be a fermionic partner to the Higgs, which has a name. It's called the Higgsino. And if supersymmetry was exact, the scalar and the Higgs and the Higgsino would have the same mass. Because the Higgsino is a fermion, it can be protected, just like the electron, by virtue of its chiral symmetry, from receiving very big corrections to its mass from Planckian physics. So the idea behind supersymmetry is to introduce a symmetry which relates scalars to fermions so that the scalars can borrow the chiral symmetries of the fermions and protect their masses from becoming super heavy. That was the original idea. Now, turns out you cannot just get by saying, okay, I want to protect the Higgs. So here is the Higgs. I guess I called it phi there. And I'll introduce another fermion. So this has spin 0. I'll introduce a fermion, which I call the Higgsino. The notation for the Higgsino is a Higgs with a tilde. So the Higgs will have a fermionic partner, which is called the Higgsino. And the Higgsino will have a chiral symmetry. And therefore, that chiral symmetry will protect the Higgs. It is not possible to just do this to the theory, just add a single fermion and solve the problem of explaining the lightness of the Higgs mass. You have to introduce a partner for every known particle, because to have the theory protect, to be able to protect yourself against all quantum corrections, you need the whole theory to be supersymmetric. For every particle, there must be a super partner to it. And that's what I'm showing here. So for every known particle, I must have a super particle. And they have funny names. Lepton is called slepton, S for super partners. Quark is called squark. And the force particles, they get an ino. Photon is photino is the super partner. The photon has spin 1, photino is spin 1/2. Gluon and W have spin 1, gluino and wino spin, I think you have to pronounce this properly. Higgs and Higgsino is similarly. So if you try to get by just by introducing the Higgs, oops, there is an extra G here. If you try to introduce just the Higgs and the Higgsino and you miss all the other super partners, then corrections, quantum corrections to the Higgs mass that will involve the photon would give a very big mass to the Higgs if there is not a photino. You need a photino, you need gluino, you need every particle to have a superpartner to shield the Higgs from getting mass. So now supersymmetry is, if supersymmetry was exact, there would be, for every lepton, for every particle, there would be a superpartner which is exactly equal in mass to the original particle. Now, this is clearly not observed. The electron mass is about 511 kiloelectron volts. There is no scalar particle with a mass of 511 kiloelectronvolts. We would know about it. It would change the world completely, chemistry. Anyway, it would be a completely different world. It's not clear it would support life. I don't think it would support life as we know it. So it's quite clear that supersymmetry cannot be an exact symmetry. It has to be broken a bit. And this means that the mass of the particle, a standard model particle, and its supersymmetric partner is not exactly equal, but they differ by an amount which is called, this is the m SUSY squared. This is the supersymmetry breaking scale. And we know from experiment today that this supersymmetry breaking scale has to be at least, of order of several hundred times the proton mass, and in some cases 1,000 times the proton mass. So the supersymmetry is not exact in nature, but if we want to explain the lightness of the Higgs mass, the supersymmetry has to be not too far from the weak interaction scale, from the mass of the Higgs particle, which is 125 GeV. So that is the reason why we expect, if supersymmetry explains this stability of the world against quantum corrections, raising the mass scale of weak interaction to the Planck mass, if we want to do it, we should discover supersymmetry at the Large Hadron Collider. That has been the logic for the last 30 years or so. And here is the way, just like for the case of the electron. You remember for the electron, there was a diagram involving the electron that corrected its mass, and then a diagram that involved the positron, the electron running backwards in time, and the two canceled. Similar thing happens here. The Higgs, for example, the top contributes a mass to the Higgs, which is very large by itself, but there is the superpartner of the top, which is called the stop, which cancels the dominant contribution to this mass and leaves us with a contribution that is proportional, that involves the difference in the masses between the top and the stop, namely the degree to which supersymmetry is broken between the stop and the top, the degree to which stop and top fail to be equal in mass, which is called m SUSY squared. So if this m SUSY, if the SUSY breaking scale is about 100 or 1,000 GeV, that is small enough to protect the Higgs. Okay, so this is the idea. There are several things that now I'm running. I have 3 minutes. So supersymmetry has several nice properties. It has a nice candidate for dark matter. It predicts this. Picture doesn't convey a lot of information to be conveyed in 3 minutes, but it has a dark matter candidate. It predicts a lot of phenomena at the Large Hadron Collider, and most importantly, it unifies strong, weak, and electromagnetic interaction at a mass scale which is about 10 to the 16 GeV, and suggests that better proton decay experiments will see. And this is to be contrasted with the standard model. That's the picture I was telling you before, which fails. The couplings fail to connect at the same place, to unify at the same place. Stay tuned on this. I mean, the Large Hadron Collider has put limits. Never mind what this plot does. It has too much information. It tells you that in the simplest possible supersymmetric theories, the masses of the supersymmetric particles have to be bigger than 2 TeV, 2,000 times the proton mass. This is all this picture says. So 2000, this is again in the simplest theories. In other theories, the supersymmetric particles can be down to 700 GeV or 600. Some of them even lighter. So this gives you an idea of how good this, the Large Hadron Collider, how well it has been testing these theories. And the search for supersymmetry has been, after the Higgs, one of its major objectives. So stay tuned, and unfortunately I have to end here. Factor of 2 of where it is, okay? This requires the existence of a multiverse of possibilities, so many, many universes, each one of which has, for example, a different weak interaction scale, which means different W and Z balls of mass. So within a factor of 2, you cannot change the scale of weak interactions. The statement has to be made more precise. It's the ratio of weak interactions to the quantum chromodynamic scale that you cannot change. So if you are willing to use such criteria, such what's called anthropic reasoning suggests a new class of theories that have some of the virtues of supersymmetry without some of the problems. So they are called split supersymmetry theories. They are theories where all the enos, the things that have to do with forces, gluino, photino, Higgsino, are like, but all the scalars, quarks, leptons, etc., are heavy. These theories have dark matter candidates. They turn out to give you exactly the same gauge coupling unification. And they also explain why we haven't yet seen any effect of supersymmetry, either from LHC or from indirect purposes, but we can still find signals by looking at the enos at the LHC. So that's the type of direction. Now, in those theories, the Higgs tends to be heavier because the Higgs gets pulled up by the masses of the heavy scalars. The quarks and the leptons are heavy and they pull up. So the Higgs mass now can be anywhere up to 165 or something. But 140 is a possibility. This was a number that floated around for a few weeks. 140, and people were dancing that, oh, we found the multiverse. So, so the multiverse type theories would suggest heavier than 125. Ordinary simple supersymmetric theory would suggest 115. 125 is sort of, no man's land. It suggests a class of theories called mini-split supersymmetry, but this is an attempt to explain why it's neither heavy nor light. So it's a theory where the scalars are heavier than the Fermions, the enos are lighter than the scalars, the quarks and the leptons, but not by a lot. Maybe they're at 100,000 times the proton mass. So those are. But this is a confusing issue. That's what they suggest. But nobody had bet on what's called the mini-split supersymmetry before data came. Because, as the theories say, well, either supersymmetry is very light or very heavy, in which case you get two extreme. This implies the Higgs mass is a 115 or maybe 160, 165. So in between is very confusing. So we'll see. That's one of the many reasons why this run of the LHC is very exciting.
Thank you.
Yes, please.
The supersymmetry also predict the unification of gravity at high energies?
The supersymmetry, as I presented it, is independent of this. Gravity has the following interesting attribute. You remember how I drew the three couplings? Strong, weak, and oh yeah, here. So in supersymmetry, the picture would look, more attractive, something like this. All three. Gravity starts out really weak. I don't think I can come that close to the x-axis. In fact, it's more convenient to draw the inverse of the couple. So gravity starts very weak and barely grows. But at high energies, gravity starts growing as you approach the Planck mass. And near the Planck scale, it grows a lot. Now, this is just a qualitative point. I mean, at that point, we should start using string theory, some more fundamental theory that incorporates gravity. But at least qualitatively, gravity can meet with these other forces. These other forces may meet earlier, and then gravity may join them near the Planck mass. So this is a cartoon that can happen. Yeah.
So,
Yes.
just a question: could this be in practical in the neutron stars? Because gravity gets so large and so heavy, so that it changes the atomic and changes the nuclear structure of particles.
Yes.
Gravity interacts with nuclear
Right.
physics.
So neutron stars are, you see, in order to study phenomena of gravity at short distances, you need directly, you need to collide particles at very, very high energy, Planckian energy. Neutron stars are very spread out objects. So in particular, the characteristic sizes of neutron stars are, tens of kilometers. And these are the scales of the curvatures are not, are nowhere near, the short distances that you need to probe physics. They are still very important. The forces are strong enough that they even crash atomic nuclei, and in the center you may have a nuke. But these are all phenomena now. We're talking about 200 MeV or 1 GeV. This is of the order of the proton mass. These are the scales you are probing, not 10 to the 19th type. Because they're still big objects. You need to go to very short objects to probe short distance.
Okay.
Yes?
Talking about the right-handed neutrino, is there a corresponding particle, or does that violate parity?
No, it is a potentially existing particle. I say potentially because, neutrinos can get masses, two types of masses. They're called Majorana or Dirac masses. And you can explain the neutrino data to date without necessarily having right-handed neutrinos in the theory. But morally, I must admit, what you write is something called dimension 5 operator. It's some fancy term, which is effectively, you have to write some low-energy physics that mimics the physics that you would have gotten had you had a right-handed neutrino at some high mass scale, 10 to the 13 times the proton mass. So this is so suggestive that this suggests there exist right-handed neutrinos, probably at that mass scale. It's, by the way, I didn't emphasize it enough. Just like, gravity, in a sense, suggests that there is no physics at 10 to the 19 GeV. This convergence of couplings suggests that there is no physics at around 10 to the 16 GeV. These are suggestions, not proofs. Neutrino masses, the fact that you get the right neutrino masses, if you imagine some physics around 10 to the 13 times 10 to the 14 GeV, 10 to the 14 times the proton mass, is also a very tantalizing statement. I think these are sort of three independent qualitative arguments that suggest there is something happening before we reach the Planck scale. At the Planck scale, I think universally we believe there is some new physics, probably string theory or some very, very important thing happening there or before. So the neutrino, I would say the right-handed neutrino morally is discovered. It's just a question, is it at 10 to the 13 GeV? Or is it at, very low energies? It could be that you get either neutrino 10 to the 13 GeV or neutrino at around electron volts, right-handed neutrino, can explain the data that we observe, that we know today for neutrino masses and mixings. And there will be some experiments that will clarify the situation. There's an experiment called double beta decay. Neutrinoless double beta decay, which actually Giorgio Grata is one of the people at Stanford that is doing such an experiment that will, for example, if he sees something, he will know that the electron neutrino has a Majorana mass. This means that if there is a right-handed neutrino for the electron, which is probably around 10 to the 13 times the proton mass, this would be almost, it would be very convincing that the right-handed neutrino is heavy. They could also be around the electron volt scale where the neutrino masses are still explain all the data that we have about neutrinos. Any other? Okay. Thank you.
For more, please visit us at stanford.edu.